Okay, very often the first section in a chapter is a very short section. The general idea, I think, in a classroom setting would be that after you have a chapter test, this assignment would be set for the students to just do on their own without any lecture associated with it. So rather than have a separate video with a lecture here, let's just do the problems. I'll make some comments along the way. So in this chapter, we're going to be looking at limits. And let's start by investigating a few of these functions that have interesting limits, okay? Let's start by graphing this. F of x is this polynomial divided by x minus 2. So this is a rational expression. It's a ratio of two polynomials, okay? Okay, I've entered the function in the input bar, and here it is. And notice the graph, at least at this scale, looks linear, and as I go out, it still looks linear, so, okay. So it looks like we have the equation of a straight line, but is it? Notice there's a problem when x equals 2. So let's plot f of 2, and notice it's undefined. So here's a function that does not have a value at x equals 2 because 2 minus 2 is 0, and you can't divide by 0. If you look at the numerator, it says 2x squared. Let's plug in 2, just try to do it in our head here. 2 squared is 4 times 2 is 8. 8 and 2 is 10. Minus 5 times 2 is minus 10, so 0. So when x equals 2, both the numerator and denominator are equal to 0. And so this is not, strictly speaking, undefined. It's what we call indeterminate. It's 0 over 0. All right. So I think we have shown f of 2 is indeterminate. By the way, why do we say indeterminate instead of undefined? And let me just give you, if you haven't seen this before in an earlier class, let's explain it now. Let's say that a is equal to something like 5 over 0. If a is 5 over 0, that would mean that a times 0 would equal 5. Is there any number which, when multiplied by 0, equals 5? And the answer is no, because 0 times anything equals 0. And so claiming that this is a number is equivalent to claiming that 0 equals 5, which is simply false. Okay, so there's no way that there can be a number a with this property. Okay. However, what if we have a is equal to 0 over 0? This is equivalent to saying a times 0 is equal to 0. So what number is valid to make this a true equation? How about a equals 1? Well, 1 times 0 is equal to 0. It's correct. That works. But what if a is 2? Well, 2 times 0 equals 0. That's also correct. 3 times 0 equals 0. Anything times 0 equals 0. So here it's not a matter of it being a false statement if I claim that a is 0 over 0. It's that any number I put in there is okay. This is not determined. It's indeterminate, not a false statement. Okay, they're making the claim here that y equals 3 is the limit of the function as x approaches 2. All right. Make a table of values for f of x at 0.001 unit intervals near x equals 2. And is it true that f of x stays close to 3 when x is kept close to 2 without equaling 2? We know it can't equal 2. So in other words, let's create a table, let's use a spreadsheet, and let's set the interval here equal to 0.001. Okay, I've started off a spreadsheet here. Here's my, just a constant is 0.001. That's going to be my difference in x. I made a column for x and a column for f of x. And here I'm going to center it on 2. And notice that's just a constant. And this is the formula. So this is 2x squared minus 5x plus 2 divided by x minus 2. X in this case being b10. So b10 is a relative reference pointing directly to the left. And now let's change this. Let's say that this cell is equal to the previous one plus this difference here, except I'm going to make that an absolute reference so that as I drag it down, it's always going to be pointing back to the same cell. Okay, so let's drag this down a ways. And up here, let's say this is equal to the following cell minus that, and then put a dollar sign in there, all right? And then drag this one up. Okay, doesn't matter how far up, okay, because we just want to see what's happening close to 2. And then this formula should apply to all of these. It's undefined at 2, but the formula is still good. There's your formula, and it's just looking at whatever number happens to be directly to the left. So notice the formula is valid for all of these values of x except for 2. And also notice that it's 2.984, and it comes down 2.994. Here's 2.998. And so forth. So in fact, it's approaching it linearly. Look at that. 2.992, 2.994, 2.9996, 2.998. This would be 2.9910. In other words, it would round up to 3 is what you'd expect. Okay, so if you look at the difference from one to the next, and if I kept that sequence going, this would predict that this ought to be a 3. However, given the formula we have, you can't divide by 0. It's indeterminate, and so even though 3 is the most plausible number to go in here, it doesn't work unless we tinker with this formula a little bit. Okay, now what if we change this difference? Let's add another 0 there. Well, we get the same pattern as we get numbers very close to 3 down here, and here's a little bit under 3, here's a little bit over 3. But it still doesn't work at this. Let's put another 0 in there. And another 0. Okay, so here's very close to 3 on both sides, but you can't let this equal 2 or we crash. Okay, so is it true that f of x stays close to 3 when x is kept close to 2 without equaling 2? And the answer is yes. Okay, how close to 2 would you have to keep x for f of x to stay within 0.01 units of 3? Okay, and then it asks in more general, how could you keep f of x arbitrarily close to 3 just by keeping x close enough to 2 but not equal to 2? Okay, you keep adding this in because the function may or may not have a value. In fact, this function does not have a value when x equals 2. Okay. We saw graphically that this equation is essentially the equation of a straight line minus a point. And I think this will be a little bit easier to work with if we do the division. That's commonly the case in problems like this. Okay, let's just do the division outright to start with and put this in a little bit simpler form. So if I divide x minus 2 into 2x squared minus 5x plus 2, x and 2x squared goes 2x. 2x times x is 2x squared. 2x times minus 2 is minus 4x. Change the signs and add. This goes away. This is minus x plus 2. X into minus x goes minus 1. And minus 1 times this is minus x plus 2. And subtracting, I get 0. It goes evenly. In other words, f of x can be factored. This is one of the factors, and this is the other factor. The denominator is x minus 2. Okay? So you might say, well, let's just cancel these, and this boils down to that. That's essentially correct, except at the one point where x equals 2. And the reason is, when you cancel, in a sense you're dividing top and bottom by the common factor. And when x equals 2, that common factor is 0, and you can't divide by 0. Another way to look at it is that this x minus 2 over x minus 2 is equal to 1. Well, that again, that's true everywhere except when x equals 2, because then you have 0 over 0. And it's indeterminate. It's not necessarily equal to 1. So in other words, this this simplification of the function is valid everywhere except at the one point, which is missing. So basically what we're looking at is the equation of a straight line. Now let's come back to the problem here. We have a straight line whose intercept is -1 and whose slope is 2. Let's consider the point here where x is 2 and turns out y is 3, because if I plug in x equals 2 on this equation, 4 minus 1 is 3, okay? And if I'm within a certain margin of error of 3, the question is, here's our straight line, the slope is 2, and so the question is, how close do you have to be to 2 to be within this margin of error on 3? If we're playing this little game where you're specifying a margin of error on the y-axis and I have to specify a margin of error on the x-axis that will put my value within your margin of error up there, we're basically looking at points within this little rectangle. And so if here is your margin of error, I want to say, what's my margin of error? And since the slope here is 2 to 1, this ratio here is 2 to 1. So to answer this first question, if the margin of error in the y direction is 0.0001, I have to keep the margin of error in the x direction at half of that. That's 0.00005. And so that would be the answer for part A. And arbitrarily, in other words, if you pick anything in general, the same rule applies, that the margin of error in x is going to have to be half as great as the margin of error in y. So anything within this margin of error on x is going to fall within this margin of error in the y. Okay? The missing point is called a removable discontinuity. Why do you think it is called that? Well, it's because we can tweak our definition of the function in such a way that everything stays the same except that one point is replaced. In fact, simply by changing this function to this function, we can say, call it f1 of x, because we've modified it. If we call it 2x minus 1, this function is exactly the same as that function everywhere except at the one point where this one fills it in and this one doesn't. So we've plugged the gap and therefore we've removed the discontinuity. Okay, I'm going to do problems 2 and 3 in parallel. Notice that the functions in these two cases are very similar, and in each case we want to know what happens when x approaches 3. Notice that x cannot equal 3 because then their denominator here would go to 0, and both of these functions have that problem. However, this function has this x minus 3 out in front, so this one is going to have a different behavior than this one. Let's look at these graphically. Okay, here is the graph of g of x from problem 2, and here is, turn the other one off, here's the graph of h of x from problem 3. Okay, and if we just explore this a bit, if I zoom in, it looks like this is approaching a particular value. It's literally pointing in at a certain value in there. And if I put a point on here and then just drag it into the middle there, it looks like that's the point 3, 2. So it looks like when x equals 3, y should equal 2. Let's see if that's true of the function itself. So let's plot g of 3. And it's undefined. So there is no value at that one point, even though it looks like the closer I get, the closer I'm getting to the value of 2 in the y direction when x gets close to 3 in the x direction. Okay? So just graphically, it looks like as x approaches 3, y is going to approach 2. And in this case, notice that the oscillation is full up and down from +1 to -1. And this has just as many oscillations as that previous one did. And so as I zoom in, it's like going into a wall here. It's having trouble plotting it in close, but notice here it's getting finer and finer and finer. And so if you gave me any kind of a limit, a margin of error that's less than 1, this is going to go, the y value is going to go outside of that margin of error repeatedly, no matter how close you get to x equals 3. It doesn't settle down to a well-behaved, limited vertical extent when x gets close to 3. So the conclusion is h of x doesn't have a limit. Let's do this one numerically as well. This is a good one to check out using a spreadsheet. Okay, here I've taken the limiting value, and I'm only looking at values on the right-hand side coming in from the right. You could equally well do this by coming in from the left. So this is 3, this is 3, plus that little difference, and that's the increment between these, okay? Over here is the function. So this is the sine of 1 over x minus 3 plus 2. And the x is, in this case, is b2, the number directly to the left. That's a relative reference, okay? Notice these are all the same, except the only change is in the b reference there. b5 is this number right here, which is directly to the left, okay? Notice that if I have small changes in x, I'm getting rather radical changes back here. This is up around 3, this is down around 1, and back and forth, okay? Let's add some extra zeros there. I added a bunch of extra zeros. And notice, look at this, it's still oscillating back and forth wildly. It's not settling into something that it looks anything like a limit. Okay? Adding more zeros. Okay, let's give some more space so we can actually see these things. So these are very, very close to 3 in the x values, but notice the y values are wildly going back and forth. Here's very close to 1, here's very close to 3, and they're going back and forth the entire time. So this function does not settle down to stay close to any one particular value as this number here approaches 3. You get as close to 3 as you want, and it's still going to have this oscillation back and forth. Okay, whether you like numerical tables or whether you like the picture, that's sort of an interesting comparison. So this does not have a limit, this does. All right? Okay, that's it for this lesson.